Hello, guys. Good evening. So, how are you all? I hope you all are all right. So, today we are going to learn most important protocol that is called serial peripheral interface, which is widely used in the industry standard protocols, which is the serial. This protocol basically convert the parallel data into the serial, right? Serial. So basically, whenever the data is coming in the parallel somewhere from the bus and it converts into the serial, like the USB module, right? These all are the serial communication protocol. USB, I2C, UART, all are the serial communication system, right? So most widely used. This is the most widely used protocol, guys. So I'm going to give you the basic idea how we can design this protocol with the help of Verilog and Verilog. How to write basically state machine. We'll be learning how to generate the clock signal, right? All the important things I'll be discussing in this module. So yeah, this is the very important for everybody and to learn the FPGA. So I'll be discussing, I'll be writing the code in a very layman language. So everybody will be understanding and everybody can write the controller, right? Okay. So guys, in the we'll be writing the SPI protocol for the zedboard. Basically, in the zedboard there is a OLED which is 8 cross 120. That is, there is a 8 row and 128 pixel in each row, right? But we'll be focusing on the part of controller. So basically, in the serial peripheral interface, there are the three channels. That is, first channel is the serial clock signal, SCL, that is called serial clock signal. We have to generate that signal and serial data signal, and another is the chip select signal, right? So these three signals mostly will be controlling the OLED. But in case of Z-board, there is a chip select signal is already connected, that is already grounded, right? So that means the our communication is always ready. Whenever in the serial peripheral interface, whenever the chip select signal is made from high to low, then the communication starts. But in the jet boards, there is already connected. Already chip select signal is made low. So we don't need to care about that things, right? So let me open my paint first of all. Okay, guys. Okay, as you can see here. So let me show you. So this is the top model we'll be designing. Okay, so let's suppose this is the module. I'm filling color inside. Okay, guys. So fill solid color. That is I am filling. Okay, let me fill how to fill the colors inside the box outline. Okay, guys. Okay, there's also so I'm going to some modules. Okay, what guys? So guys, okay, so I'm going to design first of all out module. Okay, So this is the signals we'll be having. Okay, to okay. Let me copy it. So these are the signal we'll be requiring. So first signal name is, so this is the clock signal. So this is the clock signal, and another is reset signal, and another signal that is this the data. And that in our case, there will be the 8-bit 1 byte of data will be writing parallelly. It will be coming from the another module. So this another signal will be the load when the data has to be stored. This is the load signal. Okay. So these are our input interface, and this is our serial peripheral controllers. Okay, guys. So this is our serial peripheral controllers, and the output will be, in our case, okay, so these will be the output signals. 2, 3. Okay, guys. So first one will be this is the serial clock, SCL clock signal. SCL out. Okay. And the serial SCL data signal. Serial data, and another will be the down signal. Transmit down signal to indicate that the 8-bit data has been transferred. So this is the okay. This is the top model of our design. Clock, reset data, and the loop will be the input, and our output will be the serial clock, serial data, and the external. And another signal that most of the case will be having that the chip select signal, but in our case, we do not have to connect the chip signal because it is already connected inside the zedboard. Okay, guys. So now I'm going to share the Vivado. Okay, so here we'll be designing. Here we'll be designing the whole thing. Okay, guys. So I'm going to create the new model. Create file. So we are going to write in the Verilog. So Z serial SPI controller. SPI controller is the model name. Okay, guys. I'm going to click on the next. Okay. Okay. So it is updating now. Okay, so update and it's done. So now this is the model just create it. Okay, so now I'm going to write a code. We'll be simulating this design. Okay, so I'm going to define the input ports. Let me define input block, input set signal. Another one will be the input data, that is 8-bit 7 down to 0. This is the parallel data in Okay guys, so another will be the input signals, and the output signal will be the output SCL clock, right? We just hold on output, just hold on guys. Okay, okay, so we were here. So this is the serial clock output signal and the serial data. This is the serial data output signal, and another signal is output TX down signal, right? These are the interface which will be connecting with the zedboard OLED. Okay guys, so basically here we'll be writing some state message. Okay guys, so I'm going to define. And another thing, this in the zedboard there is the 100 megahertz clock signal. 100 megahertz. 100 megahertz. This is the system clock, guys. Okay, system clock. Right. So this is the 100 megahertz system clock. That is, but the OLED cannot operate in the 100 megahertz. So we have to use we have to slow clock, right? So that maybe you can see in the zedboard OLED dataset. So it can maximum data throughput is the 10 megahertz, right? So we'll be using 10 megahertz clock signals for this 10 megahertz clock signal, right? So you are generating the 10 megahertz clock signals from the 100 megahertz. That means you can calculate. So I'm showing you just for the sake. Okay, so 100 divided by 10, that means you are getting how much? That is 10. So 5 nanosecond, this is the high, and 5 nanosecond, this is the low. 10 times, right? 10 times the smaller clock we are using in the SPI. Okay guys, so for this we are going to create the raise. So clock 10, this is the clock 10, is the frequency. Okay, just hold on. Stop. हजुर कुरा गरिहालिछ कहाँ गइरहेको छ हजुर ए हजुरलाई लिन जानुपर्छ पानी कस कसमा लिएर आइसिन्छ तपाईँमा अनि त्यत्रो कति टाढा छ ए ल ल ल ठिक छ Okay guys, so here we are here. So we'll be needing counter. Let's define the counter. So counter will be the minute to count 5. That means 0 to 4. So we need 3 bits counter. That is the counters. Okay. Okay guys, this is the counter. 255. So first of all, I'm going to generating. Yes, 10 megahertz. Right, 100 megahertz clock signal. Signal. Okay, guys. So we are going to write in the standard way. Always share the age phase or clock. That is the system clock. Begin and end. So if reset is high, begin and counter is equal to 0. Okay, guys. So counter is equal to 0. Else begin and counter is equal to counter plus 1. Okay, guys. If the reset is equal to reset high, or you can write here counter is equal to 4. You have to initialize. If the reset high and the counter is equal to 4, then you are making it low, else counter is equal to counter plus 1. Okay, so this is the counter which will be counting from the 0 to 4 only, not 5. Okay, guys. Okay, so counter design is done. Now counter is done, so we'll be assigning the clock. We share that this clock begin and okay. If counter is equal to 4, begin. If the counter is equal to 4, begin and end. Okay. As we can write here, we can write here the counter not equal to counter not equal to 4. Guys, then clock 10 less than equal to 1 tick be 0. Begin and else begin and end. Okay, here's already defined. So counter not equal to 4, that means 0, 1, 2, 3. Clock not equal to 1 tick be 0. Clock is 0, else, right? Else clock 10 less than equal to negation of clock 10. That means clock will be toggling whenever the counter will be equal to 4. Else case. Whenever the clock, whenever the counter equal to 4, then the clock 10 will be toggling. Okay, guys. Here is clock. Okay. Value is 0, 2, 3, not 4. So got it. Okay, so okay, so begin and this is the begin and then another. Here's the end. So this is done. Counters. Okay, so now we are going to write the state machine kind of thing. State machine. Okay, so here we'll be defining some states, always at the rate also. So here we are capturing the data in the negative age. so that OLED will be capturing the data in the poses. So we'll be using the clock that will be so we'll be using the clock, guys. So always have the naked Z naked clock 10. So I'll be capturing the data and the negative base so that OLED is because capturing the data and the positive base. Okay, guys, so begin and so first of all, if the reset, if somebody sprays reset signals, right? So in that condition, what will be the states? So let me define state next and idle will be in the idle state and the signal that is the so tx done and the serial data, right? So here we can write tx that's time equal to 1 take p 0 and the SCL data is time equal to 1 take p 0. In case of reset state, that is the tx-down signal and the serial data signal is the low. So to define the states here, so is state 0 to idle. By default, it is in idle state, so I am defining local param. Local okay. Idle, then will be defined the send state equal to local param idle is equal to tick decimal 0 and write like this. Idle send tick one on state tick 2. So these are the states. Okay, so these are the state. We have the three state. That means state is the size of 1 down to 0. That is 2 bits. Okay, so this was the 2 bits of the signal. So here's the TX down we are using in the procedural block. Whatever we are using inside the always block on the right hand side, if you are assigning, if you are using the signal inside the always block and we are assigning on the we are assigning to it, then we must define the signal as a register type. So here we are defining the range, and this is also range because we are using the procedural block. Initial begin and end are always begin and end. If we are using inside that block, then signal must be defined range. If we are using outside the always block, right? So then you have to define that signal as a wire type. Okay. So here is the begin. We just forgot that begin. And if the reset is not there, then begin and else is that is state. Case state. We are here in case. In case. Now we are in the idle state. Begin and end. Okay, right. So in idle state, basically we'll be checking if load is high. The load is high, then what will be the case? Okay, TX. So state first of all state will go to send state and the TX done will be the one will be 0 low HCL data and equal to 1 tick be 0. Initially this data will be the 0 and will be storing that output data. Output data will be storing in some kind of register. So here we'll be defining that register range. Okay, so 7 down to 0. 7 down to 0, we have to define shift range. Just wrote it like shift register. So okay, so whenever we press the reset, so shift range will be storing that is shift range will be date by date t0. Okay, so in this case we'll be storing here shift range less than equal to data just store output input data to a shift register. Okay, we just store this signal again. This is the end guys. Okay, idle state is completed. Okay, so now we are going to another case, that is the send state. Send state, so here begin and end. So here we'll be defining if the load is high. We have just come to the send state. So here we'll be sending the shift register data, 8 bit of data, serially to the output signal, right? So for this, what we need to do here is for this is the MSP will be sending first of all. So serial data. Okay. So guys, here I'm here. So we'll be storing the data. Shift range, that is 7. MSP first. MSP send must. Okay. Now we'll be moving shift register to the left. Shift range less than equal to so shift range 6 down to 0 because 7 bit we have shift, and in the right side we'll be adding 0, right? If we are shifting left, then we need to add the 0 on the right side. If we are shifting right, then we need to add the 0 on the right side. So this is the syntax. We have to put it on the curly brace. Okay, guys. Near the shift register, there's a syntax error. It is showing there is syntax errors. There is the column F. Okay, left. So first in the next block will be shifting the 7 bit to the serial data, and the second next, whenever the second round comes, that the 6 will be shipped to the serial data. So in this way, there will be the 8 clock cycles will be requiring. So there must be the counter as well. So which will be counting the bit. Okay. So here I'm going to define the bit counter. If bit counter is not equal to 7, okay, that's 7. Again, counter is not equal to 7. Then we'll be implementing here. So here with the incrementing else again, and so here if the bit counter is 0, 1, 2, 3, 4, 5, 6, 7, that is 8 bits transfer. Then we have to go to the next state, that is the state will be the down state, and the bit counter must be 3 bit will be the, so 3 bit 0. Okay, so bit counter must be 0 in this case. Okay, so state will be, so I'm defining here bit counter as well. So it will be counting 0 to 7, right? So here is 2 down to 0, 3 bit counter. Okay, guys. So if the reset signal is asserted, then we'll be assigning bit counter that's 10 equal to 3 to 0. Okay, so bit counter is 0 there. Okay, so now this is done, and finally we have the dawn state. Dawn state, so we can uh, and okay, so here we have the dawn state. So in this state, TX dawn signal will be the high. One tick, TX dawn is high, and we'll be also checking. And we'll be also checking over here that if the what happened done, we have the dawn state. We have sent 8 bit, right? So SPI, there must be in the case that for the some moment of the time, for the few nanoseconds, there must be the load signal low, right? So let me write if the load is low, then what will be happening again? Okay, so if the load signal is low, then the TX down will be the one take be 0, down signal is low, and will be done will be changing our state to state less than equal to idle state when the load signal is low. Okay, so this two-state machine is done. So one thing we are left here with the okay, the external signal will be the low. So one thing here you can see that the clock is on continually running, right? But in the SPI there is for some time there is clock. Clock is stopped. Whenever the data is transmitting, then only clock is started. So how can we do that, right? So we can do that because here this is the actual output port, this is the actual output port, right? So guys, so how we can do that is, let me define another clock enable signal basically, right? So we'll be defining the clock enable signal. Let me define which clock enables. Okay, so this is the clock enable signal. So whenever the reset is high, equal to 1 take be 0. Reset whenever the reset is high, then the clock enable is 0. And the idle state is also because we are not transmitting the any data. So here as well, the clock enable signal is 0. Okay. So basically here we are transmitting the data. So here we will be enabling the clock signal. To be 1. Okay. So clock is enabled now. We are transmitting a storm, so here we'll be disabling the clock. Enable less than equal to 1 tick be 0. Where we just disable the clock. Okay. That is the clock enable signal done. Okay. So here finally we'll be defining the output ports here. So here is the output serial clock. Actual output serial clock signal. So here we'll be assigning a serial clock signal as equal to. Okay guys, so a serial clock signal we'll be assigning to this clock clock 10. Okay. If how can you write this? Okay. So will be clock enable is equal to 1 tick P1. Whenever this is the clock enable signal is 1 tick P1. Okay. That is 1. Whenever the clock enable signal is high, then will be assigned to clock 10. Else will be making the clock signal too high amperage. That means will be assigned to 1 tick P1. Time the clock will be checked. So what it is saying that if clock enabled signals high, then is generated here. Else will be high. So this is also we have done this. Okay, you can if you want to define, you can define the wire of by default all the signals are wire type. Okay guys, so it's the clock signal and it's the clock which we are generating. So text and signals real data. Let me go to shift register, that is the 0 bit counter clock enable signal. We can define clock signal too because okay guys, so here we can initialize the clock. Initial begin end. Initial begin end. Initial begin and for simulation purpose we are writing, but in the hardware all the signal either it is 1 or 0. So for the simulation purpose we are defining the clock 10. Okay. So clock 10 is equal to 1 tick by 0. Clock is initially 0, clock 10. Okay. So here, okay. Now whenever the counter is not equal to 4, clock 10 0, else begin clock 10 whenever the counter is equal to 4. Okay guys, so reset is high, reset accepted, item state tx1 0, shell block data 0, shift register is the 0. Okay, bit counter this clock enable, that is the 0. Okay. And else case state, idle state, if the load is high, then the state will be going to send tx down is only 1 tick to 0. Okay guys, so still we have not sent and data serial clock signal, serial data signal 1 tick to 0 shift register. We are storing the input signal to the shift register. Store 8-bit input, 8-bit, we can write data into the shift register, 8-bit 8-bit shift register. Okay, clock enable is the 0. Still we are not started. We have not started begin. Clock enable whenever the high, then we are actually sending the data. Serial data shift register. MSP data send first shift register. So this is the 7-8-bit. Okay, so we are shifting left. MSP send 6 down to 0. One day we are adding the 0 to the right hand side because we are shifting the left. Okay. The weight counter not equal to 7, that means we have not sent all the data. That means we need to be stay in this send state till the counter equal to 7. Okay. Weight counter is incrementing 1 to B1. This is else begin done. Weight counter is the 0. Okay, and then done state clock enable will be the 0. Tx done will be the 1. If the load is 0, then what will be the state will be going to idle state and tx done will be 0. So this is the finally we have done this begin end. Okay, so this is the begin end. Any errors? No errors. Let me save this module and we'll be simulating this design. We'll be simulating this design. Okay, guys, so I have to go to the settings. Either you can go directly to the simulation, or you can go to simulation and you have to just set the top model. So I have just created the new file, that is the SPI control, right? So I've just set the top model to this file. So model top model name Z. Okay, you can just apply it. Click on OK. So it is going to update. It's going to set the top model. As you can see here inside this model. Okay, let us wait a moment. Here you can see ZSPI controller is in the top. Okay, so I'm going to simulate the design so that actually whether will be verifying our design, guys. So where the final state. Okay. So I'm going to simulate the design. Let me turn the simulation. Okay, guys, so simulation is now let us run. Okay, so here we are going to, this is the serial clock signal. We'll be going to analyzing this serial data. Okay, serial clock, serial data, and this clock signal and the load signal. Okay, so I'm going to make powerful. So we are going to give a clock of 100 megahertz. So 0, we're going to get 1. That is 100 megahertz, that means 10 nanosecond. Okay, guys, so initially we are going to reset our system and we are going to make the load signal low, and we are not going to put any data. Okay, so I'm going to run it for nanosecond. Okay, I'm going to run clock by clock, that is I'm going to run it 10 nanosecond. Okay, guys, so here you can see we have just, okay, we need to add the state as well so that it can know the state. Go to object. Here you can add the state. Add to it. Okay, guys. So here we are now. Okay, so here you can see, guys. Here you can see. So we are in the reset state. That means we are on the idle state. State is 0. That means we are in the idle state. 0, 1, and 2. Okay, guys. So bit counter is also 0. Clock enables. Okay. So the state is high. Okay. So now I'm going to make it low. Just made it low. Let me see what is going on. We have just made it low. Okay. So counter is incrementing still 0, 1, 2, 3, 4. After 4, as you can see, after 4, that is after 4, this clock signal is high. This clock signal is high, and most of the time it is going to be in the, it must be in the high state, but what is going to run for some cycles. No, no. Whenever it is going to 4, then it is only going to clock 10. Either it is going to, okay. So there is some mistake, we have written something wrong over here. What we have written. So first of all, what I am saying that this clock signal is most of the time going to the unknown state serial data. Okay, we have to define, we have to initialize specifically if we are doing simulation. So here we can define 3 tick initial values of the 3 tick t0. Also we can serial clock signal, we can define over here 1 tick p0 by default. Hmm, what it is saying? Initial value output port. Okay, yes, exactly. Okay. So counter. Just wait a minute. So here, we have done this. Sorry, we have done some mistake. So here you can write like, we can just write the counter is equal to 0 to 4. Just turn it to write counter is equal to 0 to 4, then the clock has this. Okay, that's fine. Clock, okay, 10. Bit counter is okay. Anything else we need to change? You can see. Change it. Reset is equal to counter else main counter counter plus 1. Counter is equal to 4. Less than equal to 0. Okay, guys. Counter is equal to 4, then the counter must be less to 0. Let me rerun the simulation. Just click on this. Let me check the clock. Yes. High. So let me give some data as well. A5 is the data. Load signal. Let me make the high. Okay, guys. I have made the load signal high. We're in the idle state. So now we are going to make the load signal that is low, reset signal low. Okay. So I'm going to run 100 nanosecond. Okay, guys. So we can say 0 and 3. Okay, guys. So let me show you something that's going on over here. Okay. Here. So let me show you the clock we are generating. Is it right or not? And marker first of all. This clock signal must have, because 10 megahertz clock signal, right? It must have period of 100 nanosecond. 80 nanosecond, that is not right in our case. It must be 100 nanoseconds. So what is going on? Ten nanosecond. So you can see, guys. So this is the clock signal actual, which is going to the OLED, and this is the data. So this is the data signals. Okay, and this is the data signal. So shift register. Let me show you what data we are sending. Okay, so A5. A5 means what is in binary 101. So whenever the next clock comes, okay. So initially clock is high impedance state, because here is clock enable is not high. You can see. Okay, so clock is low. That means clock is high. We have written over there. So whenever it is high, then the clock is generated. So the first next clock will be fetching the data. That means we have sent that 1. And the second next clock we have sending the 0. And next clock we have sent the 1. And another next clock we have sent 0. And next clock we have sent again 0. Next clock we have sent 1. And next clock another 0. Then another next clock that's 1. So in this way all the data. So this is the final, which is going to the OLED module. This the data signal and TX down signal is high when the 8 bit of the data is passed. Okay. So a bit of the data is passed and we're at the dawn state. So if you want to go to another state, then again you need to, you want to send another data, you have to just put it to low. Low signal must be low, and you are in the okay idle state. Let me send another data that is 5. Let me make the low signal again high. Okay, nice. So let me run for the 100 signal. So as you can see, yes. So first next clock, that is the 0 1 0 1. Again 0 1 0 1. Dawn signal is high. In this way, you can send the data from the this controller you can use to control the validity of the SPI. Okay, guys. So this is the code. Okay, thank you so much, guys.